So thank you to Trish, Subhajit, and Piet for organizing this event. It's very nice to be back in Bangalore. I've been to ICTS before, but I've seen that the trees have gotten bigger. So it looks extremely nice. So I'm going to talk about joint work with a former PhD student of mine, Konstantin Recke, who is now a postdoc in Oxford. And the topic is going to be, some very roughly speaking, this is going to be large-scale geometry of graphs and percolation. So I'll try to define everything precisely, but maybe some things will not be as precise as others. And if you feel lost, please interrupt. So so for the remaining part of the talk, what we are going to fix is a graph, is a general graph. Okay, it's countable, infinite, it's locally finite and connected. And D is going to denote just the graph distance, okay? The graph metric. So the pressing question is the following. So when does the graph G look like a metric space? So basically, when does it look like an LP space? So there are several reasons to ask these questions, right? Because LP spaces are nice to work with. Okay, so there are several ways of asking this question precisely. So one thing that we can ask for is to find, okay, can we find a bi-Lipschitz embedding? So meaning that can we find a function f from the graph to an LP space? Doesn't matter which one. If we can find one, then we are going to be happy. And if such an embedding satisfies that, okay, it's a Lipschitz function with this constant capital C, but okay, it also has to be bi-Lipschitz, meaning that this distance has to be, so the bi-Lipschitz essentially means that I should be able to push this function, push this graph linearly inside the LP space. Okay, I don't really need to compress this. Okay, so sometimes it's too much to ask for, as we'll see. One of the very nice definitions that was introduced by Günther and Kamminker, I think 20 years ago, is the notion of compression exponent. So it says the following. So the LP compression exponent is the largest alpha. Alpha can be at most 1. Can be 0, but it's between 0 and 1, such that we have to find an LP space and a Lipschitz map such that this is not quite bi-Lipschitz, but the lower bound that we get is the distance, some power law of the distance. Okay, so alpha can be strictly between 0 and 1, can be 1, can be also 0, but that's basically the definition for this. Okay, so since you might be wondering, so the compression exponent is of course, it depends on P, which LP space you find, and it just depends on the graph G. It doesn't quite care about the measure defining the LP space, right? Because, okay, I'm assuming G is countable, so you will always, we can always find the LP space with respect to the counting. Okay, does it make sense so far? Okay. So moving on, so it was, as mentioned before, it was introduced by Günther and Kamminker as a measurement of how much does the function fail to be by Lipschitz. It's a quantitative measurement of this. Okay, so let's look at some examples. So the simplest graph that we can think of is the lattice ZD. So here, essentially, I can find always this linear function, and since all norms are equivalent, turns out that ZD you can essentially push this. It's very easy to see. I'm not saying that this being 1 is a trivial fact, but for ZD it's really not difficult to see that compression exponent for any LP is equal. Okay, so So another example is the tree, the four regular tree. So maybe one can just look at this picture. Wanted to put it in the same slide, didn't fit. Okay, so what can we do? So it's the four regular tree. So it's the Cayley graph of F2 of the free group with two generators. So one trivial or very easy way to define a function is okay. So look at a function f from the vertices to an LP space of the edge set. You can define this. It just remembers. It just codes the path, the geodesic path between 0 and x, basically. Right. So if you look at this f and then look at the difference of fx and fy, then they differ exactly, precisely on the edges going from x to y. So it's not difficult to see that this object, the LP norm, is exactly equal to the Piet root of the graph distance. Good. So that's the picture that you see here. So fx just records the edges on the geodesic. Fy does the same for the geodesic between the root and y, and the vectors differ exactly on this. So what I'm trying to say is basically that since this is equal to the Piet root of the distance, then the LP, the compression exponent, is going to be at least 1 over p. So this is the least that we can do. But however, there is, I'm not saying that it's very difficult, but it's this tree, this more refined embedding of the tree into LP spaces. This was done by Tessera, and turns out that the compression exponent here is also. It's not absolutely trivial, and we'll see that there is also a rather easier proof using percolation. Questions so far? Good. So. Okay, so let's look at another example. So this is known as the lamplighter. Okay, so I'm taking the simplest example. So this means that there is a base group, so which is just, let's take Z. Okay, and in Z, on each lattice point, you can think that there is a lamp which can be either on or off. Okay, and I'll be assuming that at any given stage of time, only at most finitely many lamps can be on. So okay, so there is a formal way of, and there is a lamplighter which sort of moves between these sites and then, switches on and off the lamps, changes the state of the lamps. Okay, so this gives actually it's a very nice model to study because it is actually one of the examples. It's an amenable group. It just fails to be non-amenable, but it has exponential group. Okay, and it has very nice if you want to study Poisson boundary and speed of random walks. This is a very nice model to study. So also for compression exponents, this turns out to be this is related to the speed of random walks, as we'll see in a second. Okay, so formalizing this a little bit. So an element is a pair. So this is okay. This is an algebraic way. So if you don't like it, don't worry about it. So basically, it has every element is a pair. So there is an f, there is an x. X comes from the base, and f is basically is a lamp configuration with finite support, as I was mentioning. So the generator says, okay, move the lamplighter one step on Z on the lattice. It doesn't have to be Z. You can also think of another graph. Okay, so but simplest one is Z. You can also think of ZD if you prefer. You can think of another graph if you want to imagine, but the simplest one is the one-dimensional lattice. This already is non-trivial. Okay, and it toggles the lamp at the current position. Basically, that's the picture. Okay, so what can we do here? So we can there is always you can have a random walk on the Cayley graph of this lamplighter group. And it's actually a highly non-trivial fact, goes back to Anna Eschler, I guess roughly 20 years ago, that the speed is not linear. Okay, the speed is n to the power 3/4 for this, and that's linked to the intricate geometry of this. So note that, if it would be non-amenable, if the base group would be non-amenable, then the speed would be positive, and therefore it would be linear. So in this case, the speed is n to the power 3 quarter. So, so it turns out that if you are looking for embedding into an L2 Hilbert space, so it's a martingale argument. It's a nice martingale argument because martingale increments are orthogonal in L2, and you can show that actually the variance behaves actually linear. Okay? So if you found a function with this with this power law, d to the power alpha, then this alpha will have to satisfy this. So meaning that this L2 compression exponent for the lamplighter would have to be strictly less than. I am not saying what exactly it is. I'm just saying that it's not linear. It comes by combining the two facts that the speed is not linear and the variance has this property. And if you put that together, then actually it shows that the L2 compression exponent is actually less than. If I remember it correctly, it was computed in a very nice paper of Sofnaur and Yuval Perez to be 1/2. Many other examples were computed. The point is that you can study many examples of this kind of graphs, and there are many Kerry graphs of groups for which the compression exponent is it's understood that it's a very important notion because it has connections to theoretical computer science and sparse Kac sets and also to combinatorics. However, it's also understood that there is no no robust way of actually okay, there is a definition, but there is no tractable way of characterizing this. So far, there was no probabilistic way of characterizing actually this compression experience. And so this will be our goal. So the goal will be, okay, so we will look at compression exponents through the lens of percolation. So look at general graphs. So there will be no symmetry assumptions on any of them. But they will include, in particular, the results that we are going to talk about. They will include, in particular, Cayley graphs of finitely generated groups. But for now, there are no groups. You can just think of a general graph. All right. So, so the goal is to develop a method to actually characterize, and this will be actually the first, as far as we know, will turn out to be the first probabilistic characterization of these exponents. And the key player will be the 2-point function. We already heard a lot about 2-point function in this course, and in this one, this is going to be so all the information that we are going to see in the main theorems, this is going to be captured. And this will not be qualitative. We want quantitative, tractable bounds on the 2-point function. And those bounds actually will give you the information that you want on the compression. Okay, so right, so here will be the motto for this. So we want to build percolations that satisfy two competing properties. So we want edges to be connected, but at the same time we want the 2-point function to decay. Okay, and these two competing properties, if there is a theorem that tells you that you need these two conditions, then you have to show that actually they're not really contradicting each other. So there is a non-empty set of things that satisfy both. And if they do, then they actually characterize the quantitative bounds of the compression. Okay. So again, so it works for graphs, no symmetry. Okay, so I'm going to take a slight detour, but this is something which might be of independent interest. This is the theory of kernels. Okay, this is a purely functional analytic notion, but turns out that actually there is a simple but very powerful connection to percolation theory. So, okay, so we know what a positive definite kernels are, positive definite matrices. So I'm saying that a kernel is going to be conditionally negative definite. I'll write C and D if and only if actually for every lambda, e to the minus lambda times the kernel is a positive definite. So this is, there are different definitions of this, and my favorite one is this, because this is something that I can align myself very well coming being a program. I'll tell you why. Okay, so there is another notion. This is called measure definite kernel. Okay, so this is okay. If you haven't seen this, it might take a minute to get used to that, but the idea is actually very simple. So it says that, you call a kernel measure definite if you can find some measure space, call it omega, they call the measure mu, and a map from your space X to the Borel sets in there in omega. So the map call is X is mapped to A of X. A of X is a set such that the kernel can be represented as the measure of the symmetric difference of the two sets. Okay. So we'll see that actually this is a very simple interpretation, but in this generality, it's might be difficult to visualize what's going on, but we'll see that in a second. We'll see some very probabilistic examples of this kind of kernels, and maybe we'll have a feeling for this. So for now, I call a kernel measure definite if it can be written as a measure of symmetric differences of sets. And I will call a kernel L1, okay, if this kernel can be written as an L1 norm of the difference of these two functions. So if it's easy to see that if I have a measure definite kernel, right? So then it is just I can take fx to be the indicator function of this set A of X. Then this object is already the L1 norm of the difference of fx and fy, right? So a measure definite kernel is always an L1 kernel, right? But actually the converse is also true. It's not obvious, but there is an approximation argument, so you can prove that actually these two notions coincide, but it's better to understand these two notions separately, although we might be switching back and forth between. Any questions so far? Say again? No, I'm saying that I'm saying that there is one definition and there is other, okay? So if it is measure definite, then you automatically find an L1, this is an L1 kernel. There is an argument saying that actually you can also go the other. Yes, it will be that. So if I have a measure definite kernel, then automatically it satisfies it answers this question. I'm saying that if you start with an L1 kernel, you can show that actually it's measure definite on the same space. Okay. So this is what I was just saying. Okay, so now about the CND kernel. Actually, the CND kernels are bigger. Okay, so measure definite and L1 kernels are inside that, and every measure definite kernel is CND, but the converse implication is not true. Okay, so there's a very simple example to understand this. So of course, if you just take R2 and Z2, and then look at the L2 norm of the squared L2 norm, then clearly it is because e to the power lambda times norm squared, this is, right? It's a positive definite, so it's a CND function. But it cannot be actually measure definite or L1 because, right? Because if it's measure definite, then it has to be a pseudometric. It has to satisfy the triangle inequality in particular, right? Because it's L1 norm difference, and L1 norm, they satisfy the triangle inequality, but the L2 norm doesn't. L2 norm squared doesn't. Okay? So this is a very simple but very useful observation. Okay, so So now, okay, so now probability, what, percolation, what does percolation have to do with kernels? So I'm going to write tau, as usual, for the 2-point function. The probability that we are connected. So it's a very nice, again, simple but very nice observation going back to Eisenman and Newman from the early 80s, that actually the 2-point function is positive definite. Okay. So that's just a one-line computation that you can assign to your students. And now, so let's look at the function that is going to be very important for us is 1 minus tau. Okay. So the probability that U and V are not connected. Okay. So I can of course write this as trivially as 1, I can write tau UU minus tau UV, right? It's the difference of 2 positive definite functions. Okay. So difference of 2 positive definite functions is conditionally negative definite. Okay, maybe I should write this. So here I have all CND functions, and inside I have measure definite CND kernels, and also inside, strictly inside, I have the measure definite the L1 kernels. And so the difference of 2 positive definite functions is actually conditionally negative definite. You can check this very easily. However, what is much more non-trivial is this lemma, is that 1 minus tau is actually not only C and D, but actually it's measured. It's an L1. Okay. So, okay, I'm not going to prove this, but okay, roughly speaking, it's not very difficult proof, but roughly speaking, it says the following. So you can write 1 minus tau as the probability of the symmetric difference of 2 sets. And what are the sets? The sets are, essentially you build it from percolation. So it's the set of all omega such that U is connected to the root. Okay. And if you look at the symmetric difference, essentially you can think of them as, okay, so I look at mu to be the law of this A of U, and that allows you to see that 1 minus tau, it has to be measured. Okay, so maybe just recall this. So 1 minus tau is measure definite, also an L1. Okay. Yeah. The mu. So mu is the law of the set A of U under P. Okay, so now turns out that, okay, so there is another input. So this is, so you fix a countable set X. X can, think of X as your graph, and you look at, denote by omega of X. Okay, so we need a space, right? This was asked by Gadi. So what is the space? And for most practical purposes, we can construct the space actually in a universal manner. So it's a canonical space. So omega of X, you can think of them as all non-trivial subsets of your set X. And you define A of X, or I wrote S of X, is look at all the subsets that contain the element little x. Okay. And therefore, the symmetric difference is going to be all subsets that contain either X or Y. Cannot contain both. So another way of looking at the symmetric difference, and it's again very simple, but turns out to be quite useful, is that the symmetric difference, you can think of them as a wall separating X and Y, right? So it's partitioning your set, right? Either it can contain X or Y, and mu. So this will be a measure on basically the space of all walls that we can construct from the symmetric difference. Does it make sense? Okay, so with that, these two inputs, so what we can actually say is, so if you give me a measure definite kernel, okay, so what is the space for that? So the space for that is going to be the omega of x. So for any measure definite kernel, this omega of x is the canonical space for that, and it will have a measure mu. So there will be a measure mu such that k of x and y, right? So of course, by definition, if I will find some measure mu such that k can be written as the mu measure of the symmetric difference. The lemma says that the space that you are going to see canonically is the omega of x. Okay, so that's the walls that are canonical. And if you instead, if you have a CND kernel, then you are going to see a square root. And that's not something that you cannot do, it's a necessity. Okay, because of course there are kernels that are not measure definite, and therefore, you know, if you want to make the machinery work, then you will have to go to the square root of the L2 distance to make it an L. Okay. So, okay, so now suppose we have these two structures. So suppose someone tells us that either you have a CND kernel or a measure definite kernel. In the better case, you have a measure definite kernel. If not, then you're still going to be happy, but accept that modulo s squared. So the question is, suppose you have a kernel, can you now build percolations on this? So suppose you fix a kernel K, which is, let's say, a CND kernel. Okay, so CND kernel, okay, by this fact, we know that we can get a measure mu, but okay, it comes with a square root. So, so the kernel can be represented the square root of mu of the symmetric differences of this sets S at U and B. Okay, so what can we do if we have a measure? So we can always, you know, build a Poisson point process on this universal space. And now I need a fiddling parameter, so that therefore I have the Lebesgue measure on 0 to infinity. We'll see why in a second. Okay, so basically, I build a Poisson point process tuned in with a parameter D, which is non-negative. Okay, so I have these spaces, this omega, and I have a Poisson. You know, I see Poisson points there, and I'm wondering whether I can build a percolation on my graph. So I declare an edge open if and only if I see no Poisson walls, basically separating the two. So the number of Poisson walls that I had in the other universal space, I declare that, okay, so I need to prove that actually this makes sense. So, okay, so if you denote this to be the law of this, actually turns out that there is a monotone coupling that you can do, and omega t will be a subset of omega s if s is less. Okay, it comes from, so the Poisson has a lot of structure. Turns out that this, because Poisson also satisfies FPG, this percolation will also satisfy. But they will be highly dependent. So they will not be, there is no hope of building IID Bernoulli percolation. Okay, so so what are the properties of this percolation? But before moving on, maybe I'm going too fast. Does the definition of the percolation make sense? For the students? So I you know, if the walls should be thought of as hindrances of the larger and larger components coming up, right? So I'm saying that I will declare an edge open if I see no walls in this with this parameter. Okay. So so what are the properties of this? So of course, by definition, I'm saying that this edge will be there if and only if the number of Poisson points is 0, right? Okay, so it's a Poisson process. So I know the probability exactly. So it's e to the power minus t times the measure of this, right? So if you remember, so W is the wall separating the edge E. So it is the symmetric difference of SU and SV. So the measure of this is just going to be, okay, so it's the Lebesgue measure, T times the mu of the symmetric difference. We know that the kernel K is C and D, so therefore it comes with a square. Okay. And now it's up to us which T we want to choose. If T is chosen to be very, very small, and I have a reasonable bound on K, then I know that I can make it as high as I want. Yeah, yeah. Yes. So I have Lebesgue, I have mu times the Lebesgue measure. That's the T, yes. Because the K, look, so the K is a square root of mu, right? If you have mu, then it should be K squared, yes. Or did I put the, no, I think it's correct. Yes. Yes. Yes, yes. Oh, there's a. So you're saying that I missed a square root somewhere? I messed it up. Yeah, so it's mu of this, right? So yes, so mu is the square root of K. Maybe that's the problem. Okay. Sorry. My bad. Okay. So I definitely want to see a square root here. My bad. I'm still jet lagged. Okay. Okay. Right. So okay. So the point is the following. So I'm hoping to get a decent bound on my kernels, and then if I choose T very close to 0, and capital K is same as small k, as pointed out by Gordon correctly, then this probability on the left-hand side is going to be very close to. Okay, so what else can we say? So now let's look at connectivity. So choose, if you have a set of it's a path of edges from U to V, and I see no Poisson walls there, right? In 0 to T, then U and V are going to be connected in omega. Okay. So in particular, so I get a lower bound on the 2-point function that this is going to be larger than e to the power minus t times that. And that is going to be, I can get a kind of a uniform lower bound by passing to the supremum over all neighbors in here. So I get a lower bound e to the power minus t times delta being defined here, times the distance. And a similar argument tells me that I can get a similar upper bound with e to the power minus t times square. So the theorem is telling us, so if you give me any CND kernel, okay, then I can build a general percolation satisfying the properties that you want, such that two important properties hold. It has very high marginals, okay, but it has it's a stretched exponential decay of the 2-point. Does the construction make sense? Okay, so actually it's not very difficult to see that, okay, so I was telling you that I was working with a kernel here, so there was a necessity to take a square root. But if I had a nicer kernel, then essentially exactly the same construction will work, except that you will not need to, will not need a square. It will just be. Finite clusters. So amenable means finite clusters. So what is the question? Yes. The BLPS criterion? Yes. So the BLPS criteria, let's try to, okay, so it says that it's a graph is amenable if and only if you can build, now, but you need an invariant percolation. No, no, no. That's the whole point. There is no symmetry assumption on any of this. The percolation is not invariant. Yeah. Say again. Yes. So I'm saying that, okay, so if I understand your question correctly, so I'm saying that, okay, so you have two properties here, the first and the second. The first is saying that the probability that an edge is open. Right, so this tells you what exactly that probability is in terms of the kernel that you start. So, okay, so maybe the confusion comes from, the question comes from the fact that, okay, how can it be that this has large marginal and at the same time the 2-point function decays? Is that what you're asking? I'm saying that, I have a law, I have a rule that tells me when I can draw the edge. If I don't find walls. Yes. Yes. No, it should be a large. It's a lower bound that I. It's like, are you saying that the, okay? So you're saying why this is an equality? So I hope I'm not saying something wrong. I guess yes. What you're, if you can, I think, okay. So 1 and 2 are not contradictory, but I hope I'm not saying something wrong. But you can put them together, and then what you're saying is good. Yeah. Yes. 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 No. So I'm saying that it will. I'm saying if you have a Cayley, if suppose, okay, so there is an invariant version of this theorem as well. So it says that if you have a finitely generated group, then I'll go to the theorem in the next slide. Then there exists a percolation on the Cayley graph on. So I think if I understand, maybe I miss. So I think Gadi was asking why it does not. So if the percolations are invariant or not, right? In the constructed one. Okay. So B. Okay. Yes, I think you're right. Yes. Right. So the 2. Okay. So the BLPS was about invariant, but okay, it says that there are no finite clusters, right? That's the amenable criteria, non-amenability characterization. But here we are talking about the 2-point function decay, right? So this is what Franco, you're saying, that it can happen that the 2-point function decays, but they are infinitely many infinite. Sure, that happens on the tree, right? So as soon as you go supercritical, the 2-point function has an exponential decay, but you have infinitely many infinite. Go on. Okay, so are there other questions, doubts? So how much time do I have? Okay. Okay, that's fantastic. Okay, so now coming back to compression. So this is the that one step was building the percolations. So the theorem that you can say about compression is the following. So it's a characterization. So it says the following. So this is the maximum. So the alpha 1 star is the compression exponent is the maximum alpha, such that there exists a bond percolation with, for every p as close to 1 as you want, you can have high marginals, but the 2-point function bound is the following. So this is the key quantity. So, and these two will have to be taken into account simultaneously. So you have a lower bound with this beta constant times the distance, but an upper bound with a power. Okay? And the power is basically the alpha, the best alpha that works for you is the compression exponent. So this is the quantitative information that you can milk from this. Okay, so the idea for this is not that difficult but okay, I mean, carrying it out maybe is not okay. But the basic reason why it works is this fact in here. Okay, so if there are two parts of the theorem to be proven, right? So if I give you a kernel, then we have a recipe for building percolations with the properties. And that basically works along the lines that I described in the last slide. But perhaps more interesting is the converse direction, because this is a characterization. So if you have these properties, if you can build a percolation with the properties, so if these kind of properties happen, then there is a recipe to build a kernel, and the reason that you can do is coming from this the property of the 2-point function. Okay, if I'm happy to talk about this, how to do that with you if you're interested, but maybe not here because it gets too technical. Okay, so this was about L1 compression. So yeah. Yeah. Which one? No, that's not what I'm saying. So if so this theorem doesn't have anything to do with FKG. I'm saying that if you had a kernel, nice kernel, then the percolation that you can build will satisfy FKG. Does that make sense? So this, So the previous theorem in here, I'm saying that if you have a kernel, then you can build a percolation with FKG. The compression characterization doesn't have, I'm not saying anything about it. Other. So far, okay, maybe, so far we talked about L1, but you can also talk about LP compression. So the thing that we can say is, so if you have a kernel, then essentially we can run the same. What happened now? What did I do? Huh? Press the wrong button, right? Oh, boy. Okay, so this is where I was. So for LP, you can get a bound on this, but I'm not saying that we have a characterization of LP compression. Okay, so far the technique works for L1, and it goes back to the fact that this square root. Okay, if the square root would not be there, then I think one can do quite a bit. But however, if you're interested only quantitative bounds on the compression, you can get it from the LP compression, then you can get it from the percolation. Okay, so the problem is in the converse direction. So if you have an embedding, then the kernel that you want to build from this need not be measure definite. Again, the same problem that we mentioned earlier pops up. However, if you are between 1 and 2, then it's still conditionally negative definite, but then you have to live with the square root. But in general, we don't have a characterization for LP in general, but for L1. But nonetheless, quite some information can be milked out on that. Okay, so also there is, I didn't talk about it, but you can have a characterization of when can you embed a graph into a Hilbert space in a coarse manner. So this has quite some background in coarse geometry, why you want to do that. And percolation gives you a characterization of this along the similar recipe. And okay, so this was the first probabilistic characterization of compression and coarse embeddings. So once more, so this is no symmetry assumptions are made, and works for general graphs. Now I don't know how to. I don't know how I can show the last content for this, but okay, that works better. Okay, so this is perhaps the takeaway from this. So I was always saying that no symmetry, but the concrete examples that where we have the information on the 2-point function, we know if you give me like concrete examples of groups, for instance, pre-groups, F2, I was telling you that the compression is 1. There's a precursor to the result that I'm talking about, also with Konstantin. They are for groups. And for them, actually, you do know the decay that is exponential of the 2-point function is exponential. And you know exactly how large the marginal needs to be. And also similar examples, so the isometric group of the hyperbolic plane, the lamplighter, so for free groups and stuff like that. So for them, you have explicit bounds on the 2-point function, okay? And you can put the two theorems together, or the theorems that we have here and the characterization that we have here, and you have explicit information on the compression exponent using percolation. Okay, so that's one thing, and okay, so that gives you bounds on the compression exponent from the decay. So that's all I wanted to say. Thanks for listening.
Okay, so let's thank Chiranjib. I think we have time for maybe 1 or 2 quick questions, but we have a coffee and so you can just ask more. So any quick questions? Yeah.
No, it depends on, I think it depends just on the graph. So, but I'm, okay, no, maybe I should be careful. So I'm fixing the graph along with the graph method. So a priori, I think it could, but yeah.
Other questions? Maybe on Zoom, are there any questions? No? Okay, so let's go for tea and let's thank Chiranjib one more time.